In the last video, I left you with this example like usual. That seems like what I'm doing all the time, right? And I told you go attempt it, see what you can come up with. So let's double check your answer, or let's stop having you to be a cheater and just kind of eavesdropping on the discussion that we're about to have. All right, so here we have an alkyne, and we are reacting it with maybe multiple things. And we want to end up with the molecule that you see to the right-hand side, E2-pentene. So how do we get to this point? This brain teaser, this puzzle. How do we actually end up getting to there? All right, so first off, number one, you know you're going to have to elongate a chain. I mean, come on now, folks, right? We start off with 2 carbons here. And over on the product side, we have 1, 2, 3, 4, 5. You have to elongate a chain. So we know that amide is going to have to show up at some point in time in the synthesis product, and we know that some type of alkyl bromide is going to have to show up as well. So that I already have in my mind, right? I know that has to go forward. Next, a triple bond has not been fully destroyed. What I have in the product side is a double bond, so I don't need to go all the way. And in addition to that, it looks like these hydrogens that I have maybe added onto the molecule, they are pointed in opposite directions. So they are giving me the E form or the trans form. Either one of those would have worked here. So I'm going to have to pick a route that will ensure those hydrogens go on to the molecule on opposite sides. We know how to do that. We have that option. So let's kind of think about chain elongation first. Here's a carbon in a triple bond, and there's the carbon in the triple bond. So over here on the right-hand side, it looks like there's my double bond. So this better had been the carbon in the triple, and that had better been the carbon in the triple. I know how to take a triple to a double. That's just adding H2 onto it. Oh, well, look, H here and H there. That kind of makes sense. But those are the locations of the 2 carbons in the triple bond, which means that in my chain elongation, I'm going to have to do 2 rounds. I'm going to have to elongate it on this side, and I'm going to have to elongate it on that side. And there's my 2 additions. All right, so clear the screen. I'm going to take my starting reagent, which is acetylene again, or ethyne. I'm going to react it with NH2, and this time I'm just going to write the alkyl bromide on the arrow. I'm not going to separate them. And I know that to the left-hand side, I need to elongate that chain by 2 carbons. I can do this. This is a short-handed way of doing it. I think I've done the other way long enough that you feel comfortable with that. So this is going to give me CH3, CH2, carbon, triple bond, carbon, hydrogen. All right, so there's that. Step 1. Step 2, we said we're going to have to elongate on the other side as well. Okay, because I've got an extra carbon on that side. If I want my C's that are involved in that triple bond to really be in the perfect location, then I'm going to have to bring in another round of chain elongation. And this will give me CH3, CH2, carbon, triple bond carbon, and then CH3. So there's that. Getting closer, right? Here's my triple bond. I've got an ethyl to the left and a methyl to the right. Look at this. Here's my what would be triple bond. I've got an ethyl to the left and a methyl to the right. Now I need to destroy the triple bond to a double. And it looks like I'm going to have to add hydrogens on opposite sides. So how do we do that? Well, I'll take that alkyne. We've talked about this. This is not new. I'm going to take the alkyne, and I'm going to add to that sodium, ammonia, And you can write negative 78 degrees if you want to. If you leave that off, I'm going to give you credit for it. No big deal. So when that happens, my triple bond does break. I'm going to rewrite my reagent, like always, just to have a starting place to go. So my triple bond does break to a double. Two sides of attachment open up, there and there. The sodium and the ammonia allow two hydrogens to go on, one on each one of these carbons. So a hydrogen is going to go on here, a hydrogen is going to go on there, and folks, it goes on trans, and that's exactly what we need. We need them on different sides, not the same side. If I did H2 Lindlar would have put a hydrogen to the left and a hydrogen to the right. It would have done that, but it would have done them on the same side, and you would have gotten cis, not trans. In other words, Z and not the E form. So once I do the sodium and the ammonia, guys, that's all that we really need, right? So what they have done is that they have taken this structure, they focused on that double bond like this that we've seen before, and they draw the legs just like we did in the alkene work, and they've pointed hydrogen up on one side and hydrogen down on the other. Perfectly okay if you flip them around. As long as they're on opposite sides, that's all that matters. And then on one of these carbons, I have the ethyl group, and on the other carbon, I have the methyl group. Folks, that's what we're after. Now, I've drawn this a little backward, but I did it for a reason, because that means the same thing here. No difference. My ethyl and methyl are on opposite sides. And here in the drawing, my ethyl and methyl are on opposite sides. The two hydrogens, they are on opposite sides. And here, two hydrogens, they're on opposite sides. So this is E2-pentene. And guess what? This is also E2-pentene. You want that review? I give it to you. Longest carbon chain, 1, 2, 3, 4, 5. Pentene. There we go. Where's that double bond located? I don't number to the left. If I number to the right, that's closer. 1, 2, 3, 4, 5. So on carbon number 2, that is where the double bond position is at. If I look at the hydrogens, I've got one here and I've got one there. They are on opposite sides of that double bond. There is only one double bond at play. So I can just simply write the word trans to pentene if that's what I want to do. Or I did say E or Z could also be used for cis and trans, right? Cis and trans is kind of old school. It's really given to just hydrogen only, but E and Z can actually include everything. Z groups are not on Z same side, so this is not a Z. This is an E form, and that's exactly what we need. So I can write E2-pentene, or I can write trans 2-pentene. And either one of those are accepted, and either one of those are correct. All right, so this one's not too bad, maybe, hopefully, I hope. Ethine reacts with sodium amide in the presence of ethyl bromide to give us 1-butyne. 1-butyne reacts with sodium amide again, this time in the presence of methyl bromide, in order to give us 2-pentyne. Then 2-pentyne reacts with sodium and ammonia in somewhat of a hydrogenation reaction in order to give us the trans 2-pentene molecule that the product or that the question's after. Okay, a lot of words, a lot of verbiage, a lot of foreign language. There you go. That's the world of organic. All right, just when you think there was enough, let's take a look at this last set of problems. Yes, that's what I said. Last, I said it. We're almost finished. A, B, C, D, E, F. It says, how could the following be synthesized from acetylene? Oh, God. Acetylene. They want me to start here. Every single one of those, that's where they want me to start. So let's look at A. All right. So A is going to say this is the product that you need. CH3 CH2, CH2, carbon, triple bond, CH. And every one of these, this is where they want me to start. All right. So I'm going to take my 2 carbons. I need to react it with something in order to get this. Well, it looks like the only thing I've done here is elongated a chain. My triple bond's still there. I didn't add on any kind of group at all. So this maybe is not too bad. I need to add on the amide, of course, in order to give me the elongation step. And just to make it kind of match from up above, that's just what I'll do. Maybe it's easier to see. I'll do that first. And now we need to take that ion and we need to add something on it. How many carbons do I need? I need 3 more. So I'll add CH3, CH2, CH2, Br to that ion. That elongates the chain for me. So I'll end up with CH3, CH2, CH2, carbon, triple bond, CH3. Keep in mind the mechanism. Nucleophile is attracted to the electrophile, which is right there, and there's the key connector step. All right, so that's really all that we got to do with this one. We just add sodium amide to it, and then we elongate the chain with propyl bromide, and that will give me a product that they were after. That's all that they wanted here. That was it, nothing more. Good news. All right, next one. CH3CH2. That points down. Oh no, points down. They're setting me up for a cis transition. Just got to keep that in mind. Double bond carbon. And then here they'll do a CH2, CH3, and a hydrogen that points down. All right. So they want me to start with acetylide. Carbon, triple bond, carbon. There we go. I know that I'm going to have to elongate the chain at least. Well, I need to look at this. How do I elongate the chain? Triple bond, there's a double bond. So therefore, these 2 carbons that are involved in the triple, it's probably the 2 carbons that are involved right here. Only thing I've done is taken the triple, I've broken it once to give me a double. All right, so with that in mind, how do I elongate the chain? Well, I'm going to add amide to it, and I'm going to elongate the chain on the left-hand side first. So that means CH3, CH2, Br. In doing that, I'll rip the hydrogen to the left off. I'll have CH3, CH2, and then the carbon, triple bond carbon with the hydrogen. Now I need to do it again because I've got an elongation that happens on the right. If I need to keep that triple bond in the middle the way that it is, this is what I have to do. So I'll add another round of amide with another round of ethyl bromide. And now I'll rip the hydrogen off the right-hand side. And I end up with this. Getting closer. Now I'll take that triple bond. I need to break it to a double. So if I just break it to a double and don't add anything else on, then I can just simply do that with hydrogens, right? And that's what's represented in the picture from up above, hydrogens. Those hydrogens, though, are on the same side of the molecule. So those hydrogens need to go on the same side, which means that at this point, I can take the alkyne that I have now from up above, and I can add H2 Linlar to that, and that will destroy the triple bond to a double and ensure that the hydrogens go on to the same side of the molecule. All right, so there's my 3 steps. I'll take acetylide or acetylene. react it with sodium amide with ethyl bromide to give me this molecule, 1-butyne. 1-butyne will then react with amide again and ethyl bromide to give me this molecule, which is 3-hexyne. And then 3-hexyne will react with H2-Lindlar in order to give me this 3-hexene, but that 3-hexene is in the cis position. All right, so there's that one. Part C. CH3, CH, double bond, CH2. We have to start here. How do we do it? Okay, so it looks like this is probably the 2 carbons involved in the triple bond here on the end. So it looks like I'm going to have to elongate a chain, but I only really have to elongate it once. So this is pretty good for me. I feel a little bit better about that decision. I'll elongate it on the left-hand side just to make it mimic what's up there. So I'll do this one in separate steps. Sometimes people need that. That's perfectly fine. Not a big deal. All right, so there we go. There's the first step of the chain elongation. And then I'm going to take that piece and I'm going to react it with methyl bromide. And that will put a methyl group over to the left-hand side for me. All right, so I'm getting closer. At this point, I have a triple bond. I need to take it to a double. It looks like the only thing I've added here were hydrogens on each side, one to the left and one to the right. So it doesn't really matter cis or trans. It doesn't specify. And the reason is because it can't be cis or trans, because I will end up with 2 hydrogens on the right-handed carbon. So no matter what you do here, you're going to end up with the same answer. If you give me H2-Lindlar or if you give me sodium and ammonia, well, the same thing happens. That triple bond is going to break to a double. There we go. 2 sites of attachment open up here and here. A hydrogen goes on to the left and another hydrogen goes on to the right. So there is the condensed structure, and that's exactly what I need from up above. Right? So once again, no cis or trans, and the reason is because this carbon has 2 hydrogens, one that points up and one that points down, and you cannot rank those, people. You can't do it. Next, CH3, carbon, CH3, chlorine that points down, a chlorine that points up. Okay, you ready for this one? Can you do it? I hope. We have to start here. So I know I'm going to have to elongate it. Going to have to do it. Which side do I elongate on? Here, it doesn't really matter. I only have 3 carbons in the long chain. I only need to add 1 onto it. So I don't really care which way that you decide to elongate it. I'm just going to elongate it on the right-hand side. So that's just kind of what I do with these most of the time. So there's the first step. And then I'm going to react this with methyl bromide. And that will give me this H, triple bond, 2 carbons, and then a CH3. All right, so there's kind of the first round of additions. Amide, methyl bromide. Now I have the appropriate number of carbons. So from there, I'm going to take this H, carbon, triple bond, carbon, CH3, and I need to figure out how I can get 2 chlorines onto the same carbon. Do you remember what those were called? They're kind of twins, aren't they? Gemini. Geminal. They are geminal dihalides, or dichlorides in this case. So I can't really add Cl2DCM because that will put chlorine on one and chlorine on the other. So that's not going to work. So I need 2 rounds here of something that will add chlorine on. I hope that you will tell me HCl. If so, good for you. And C triple bond C with a CH3. And then this triple bond will break. 2 sites of attachment open up. When they do, hydrogens play with other hydrogens. Markovnikov reaction happens, so hydrogen goes to the left, and that forces chlorine to go here. And then I'm going to react it with HCl one more time. And then if I do that, I'll redraw my reagent, and here they are. Here it is. So HCl gets added on. HCl breaks the double bond. Two sides of attachment open up, there and there. Hydrogen plays with other hydrogens. It goes to the left-hand side, and chlorine has nowhere to go but there. Folks, there you go. There's the formation of that product. I add sodium amide first with methyl bromide to elongate the chain. Then I take that alkyne, I react it with hydrochloric acid to give me the alkene, and then I react with hydrochloric acid again in order to give me the alkane. I can go through and name these if I want, but we're not going to waste that time. We're just going to truck on to the very next one. All right, so for the next one, E maybe. This is what they want. CH3, CH2, 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 carbon, double bond, OH. And they want me to make this from a 2-carbon piece. All right. Let's see what we got. What's in you? Can you do it? Okay, well, we know we're going to have to amide it. I mean, it seems like that's the only thing that we do anymore. Just slap amide, elongate, 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 elongate. I mean, it seems like everything that we do, that's what's happening. At the same time, it seems like my C double bond O is here on the end, which is probably a good sign that this carbon, because that's where my piece is at that I need to add on, it's probably a good sign that these are the 2 carbons that were involved in the triple bond. So this carbon and this carbon needs to be here at the very end. So this will give me a way that I can kind of predict how I need to elongate. I need to elongate on the left-hand side here, nothing on the right-hand side. So I need to elongate first, and that creates the ion that we can draw here. And then I need to bring in propyl bromide this time. So I need those 3 carbons over to the left-hand side. So these 2 things will come together. Marriage made in heaven. How sweet. CH3, CH2, CH2, carbon, triple bond, carbon with a hydrogen. All right, so I'm getting closer. I now have the appropriate number of carbons. Now I need to figure out how to get a double bond O. Well, how do I get a double bond O? We know that this was probably an OH on a carbon that had a double bond on it at one point. All right, so an enol had to form. An enol will rearrange to that C double bond O if we can get it to happen. So how do we get an OH group onto a molecule? That's going to be my next step. Oh, well, water acid. But if water acid goes on, the O is going to go to the left-hand side. Hydrogen plays with other hydrogens. Mercury. Well, if mercury went on, OH would still go left-hand side. Hydrogen still plays with other hydrogens. The only way that we can get this to go on backward, anti-Makovnikov, if we bring in BH3, THF, OH, H2O, H2O2. That's the only way that this will work. When we do that, I'll take my reagent, CH3, CH2, CH2, carbon, triple bond, CH. And this breaks the triple bond to a double. 2 sides of attachment open up here and here. Hydrogen normally plays with other hydrogens, but not in a borane addition. It goes on the opposite carbon, so that goes left-handed, which is where we need it. And then that forces my OH group to go here. I don't have to do anything to it at this point. That enol will quickly rearrange, and it goes to the product that I need. My double bond turns into a single. The double bond shifts between the carbon and the oxygen, and I erase the hydrogen. A enol formation and tautomer begins to happen at that time. All right, so there's the answer to that one. Are these getting easier? I hope so. Are you getting more comfortable with these than the first time that you saw them? I hope that you are. All right, so finally, we have a CH3, CH, CH3 with a Br. How do we get this? How do we get it starting from here? That's what they want me to do. 2 carbons, I need 3. Doesn't really matter how I add them then. Okay, that makes that job a little bit easier. So I'll just go ahead and do this in one swoop. I'll just do NH2- and CH3Br. We'll add it to the right-hand side. That's okay. So carbon, triple bond carbon, and then we'll have a CH3 there. So NH2 removed the hydrogen, and the methyl group went on to that spot. So I've elongated proper number of carbons at this point. So I'm going to take that new product. I need to do something to it in order to get here. Well, what can I do? It looks like they've added bromine onto this, right? Okay, well, I can add bromine on. That's not a problem. HBr, only one bromine's required. So I'll start with my reagent, like I normally do. The triple bond, there we go, to a double. Two sides of attachment open up here and here. H plays with other H's, so it automatically goes left-handed because that's where those hydrogens are. And that forces my bromine to go here. All right, well, we're closer, right? My bromine's in the right position. Everything went according to plan. The difference now is that I've got a double bond, and up above I don't have double bonds. I have single bonds. How do I get rid of that double bond? Well, I'll take that product, which is my new reagent now, and I need to get rid of that double bond, so we'll hydrogenate it. Not a big deal. I don't need Linlar. I don't need any of that. It's an alkene. It's going to happen in one step anyway, so H2 and platinum is going to be perfectly fine here. And that molecule will destroy the double bond, turn it to a single. Hydrogen goes on one side, and hydrogen goes on to the other. And folks, there's your product. Okay, so that's how we do multi-step synthesis. It's a long journey, isn't it? It's going to take some practice. It's going to take also you knowing for sure all of those other reactions that we have talked about in the previous lecture modules. All of the alkene reactions, like that epoxide one that they just randomly threw into the picture, all of those are fair game. A lot of times there's overlap between alkenes and alkyne reactions. That's great. That's good. That's what we like to see. But multi-step synthesis is the beginning of failure for many people, but it's not going to be for you. In the beginning, they might be rocky. In the beginning, you might have trouble with them. In the beginning, you might have no clue what to do. And that's okay. That's normal. That's natural. But we're going to keep doing these over and over throughout the upcoming lecture modules, and we're going to get more and more comfortable with them. But folks, we are wrapping up Alkyne family with this video. So good luck on the Blackboard assignments. Good luck on the upcoming tests that will come around with this material. Again, if you have questions, you know how to get a hold of me. I say this at the every last video of every lecture module. I say the same thing. And I really do mean it. So contact me. Give me the questions. Take advantage of all your resources. And if that means going and getting a tutor, a free tutor, you don't even have to pay for it. Somebody else is paying for it. You're not. Then take advantage of that system. Don't let this material slide to a point where you have dug yourself a hole so deep that you cannot crawl out of it. Be proactive. Even if you think that you do not need a tutor, but there's a little bit of inkling where you're like, oh gosh, I don't know about this. Go get a tutor. It's better to start early than not at all or until the last minute. But I think that you're going to be okay. You're going to do this. Again, go back and remember those explanations are big words. Were those explanations okay? If so, then you are learning. You are not struggling in this class. You are learning this material as we go. You just maybe didn't realize it up until that point. So have fun with alkynes. Have fun with the Blackboard assignments and those questions. Keep in mind that they do like to get tricky sometimes. Just don't let them trick you up. And I'll be here when you need me.